Hi, I'm Valentin Wüstholz and I'm a researcher at ConsenSys. In this talk, I present Harvey, a Greybox Fuzzer for smart contracts. This is joint work with Maria Christakis from MPI-SWS. These days, major smart contract hacks are happening every few months. This is partially due to the fact that systems are becoming increasingly complex, especially with contracts starting to depend on other contracts. This can make manual testing difficult and time-consuming. Luckily, fuzzers such as AFL and libfuzzer have been very effective in uncovering bugs in regular software. Catching bugs before deployment is crucial for smart contracts. And in 2017, we started to develop a fuzzer for contracts that run on the Ethereum virtual machine. Roughly a year later, Harvey was acquired by ConsenSys and became one of the tools that power our MythX analysis service for smart contract developers. These days, it's regularly used during audits and client engagements to check complex correctness properties. Today, I will give you an overview of two interesting challenges we encountered along the way and present novel techniques to address them. First, however, what is Greybox fuzzing? Greybox fuzzing is an automated test case generation technique that uses lightweight coverage feedback to guide the fuzzer. It does not use any constraint solving, which allows it to explore hundreds or thousands of concrete inputs per second. Now let's apply this to smart contracts. On a high level, a user provides the fuzzer with an initial state that includes one or more contract accounts. A user may also provide some correctness properties that should be checked. Now it's the fuzzer's job to generate sequences of transactions that invoke the contracts under test. The fuzzer may want to mutate the transaction data, such as a function's inputs, or mutate the sequence itself. This diagram illustrates the execution model more clearly. All sequences start from the initial state S0, and each arrow represents a transaction to a new state. There can be an unbounded number of transactions from an unbounded number of different senders. And as you can see, even without considering all the paths within the code, you may end up with lots of paths to explore. After this high-level overview, let's look at two challenges we encountered when deploying Harvey. The first is well known in the fuzzing community. In this function, it is very difficult to generate an input that exercises the path that returns to through random mutations. To address this issue, we developed a novel input prediction technique. The key idea behind input prediction is simple: to make Greybox fuzzing slightly more white. More specifically, we collect additional feedback when running inputs, and we use the feedback to suggest new inputs. For each branch, we record how far the execution is from flipping it. In the literature, this is also known as the branch distance. The following diagram illustrates this more clearly. The fuzzer mutates and runs different inputs, and by collecting additional feedback, our input prediction component is able to suggest new inputs. And ultimately, this may allow us to increase coverage. Let's look at a concrete example. Assume we run the following input. What's the distance for flipping the highlighted branch? 42. Now let's assume that the fuzzer changes only input A from 0 to 7. Again, we can determine the distance for the highlighted branch. It turns out to be 35. Now, what can we learn from such feedback? For one, we can observe that the input A taints the branch. But how can we use this to suggest a promising new input value. In particular, what would be a good input value? Well, an input value that would make the distance 0 would be ideal. This problem may sound familiar. It's essentially root finding, and there are many well-known algorithms for doing so. In Harvey, we use a very simple iterative method to roots finding. It's called the Secant method. It does not need any derivatives. After all, the function is essentially the program and not a nice mathematical function. The Secant method approximates the function using a line through the two data points P1 in red and P2 in orange, and determines the point where the line intersects with the x-axis, where it becomes 0. In this case, it's for x equals 42. It's precisely the value we need to explore the highlighted branch. But wait, what if the distance function isn't linear? We can actually apply this method iteratively. And this works even for the scary looking branch condition you see on this slide. But in practice, interestingly, one step is often enough. Let's look at some of our experimental results for 27 real-world smart contracts. Harvey with input prediction is able to find bugs orders of magnitude faster and is able to increase coverage by up to 3x. Let's look at the second interesting challenge. Contracts contain persistent state, such as the variables x and y in this example. Functions can modify the state. For instance, function inc_x increases x by 1. To trigger the assertion violation in function var, we need multiple calls. For instance, 42 invocations of function inc_x. Finding such deep vulnerabilities is difficult, and we developed a new technique that we call demand-driven fuzzing. The main issue is this: fuzzing long sequences is expensive. There are many inputs, it takes a long time to execute them, and the number of paths grows very quickly. The key idea here is to only fuzz long sequences if it may increase coverage. However, there's a small issue. Increasing coverage is very easy if paths may span multiple transactions. Just add a new transaction, for instance. For this reason, Harvey only considers the path through the last transaction, and all previous transactions are responsible for setting up an interesting state. How do we determine if coverage may increase? We use something we call aggressive fuzzing. The main difference is that aggressive fuzzing can mutate the persistent state directly. In our example, this would allow it to mutate x and y. The following diagram illustrates how we use aggressive fuzzing. We enable it with a small probability, and if we observe a coverage increase, we consider longer sequences when performing regular fuzzing in the future. Let's look at some more results. We observed that roughly 60% of all bugs require multiple transactions. This shows how important deep fuzzing is. Harvey with demand-driven fuzzing was able to find bugs orders of magnitude faster and was able to achieve significantly higher coverage. I have presented Harvey, an industrial fuzzer for smart contracts that uses several novel techniques to boost its effectiveness. Check out the paper for more details and go to mythex.io to give it a try.